Hi everyone. The lesson for today is industrial buildings. Therefore, at the end of this session, students should be able to number 1, identify components of industrial building. Number 2, identify points to be considered while planning industrial building. Any building structure used by the industry to store raw materials or for manufacturing products of the industry is known as an industrial building. Industrial buildings are generally used for but not limited to number 1, steel plants, number 2, automobile industry, number 3, utility and process industry, number 4, thermal power stations, number 5, warehouse, and number 6, assembly plants, number 7, storage, number 8, garage, and etc. Before selection of any site for industrial building, there are several factors that need to be considered. Number 1, the site should be located on an arterial road. Number 2, local availability of raw materials. Number 3, facilities like water supply and electricity. Number 4, the topography of the area. Number 5, the soil condition with respects to foundation design. Number 6, waste disposal facilities available. Number 7, transportation facilities. And number 8, sufficient space for storage of raw materials. These are the major components of industrial unit. Number 1, roof sheet. Material used to cover the shed is known as roof sheet. Number 2, roof trusses. A structure that is compound of a number of line members pinned connected at ends to form a triangle form work is called truss. Number 3, purlin. A member supported on the panel points of two consecutive roof truss is called purlin. Number 4, girts. Girts are the secondary structural member which provide support to roof and wall covering and also transfer wind load from wall material to primary frame. Number 5, eave strut. The member located at the intersection of roof and exterior wall is known as eave strut. Number 6, bracing. A member which transfers horizontal load from the frame to the foundation is known as bracing. And number 7, wind bracing. Two roof trusses are connected by cross member to stabilize it against the action of wind. Such members are called wind bracing. Prior to planning and designing industrial building, there are several points that need to be considered. Number 1, selections of roofing and wall materials. Roofing material is used to cover the roof of truss. Corrugated galvanized iron or GI sheet are usually adapted as coverings for roof and sides of industrial buildings. Light gauge cold form rib steel or aluminum decking can also be used. Sometimes asbestos cement sheets are also provided as roof coverings owing to their superior insulating properties. In selection of wall system, the designer should consider the factors such as number 1, cost, number 2, interior surface requirements, number 3, aesthetic appearance, number 4, acoustic and dust control, number 5, maintenance, number 6, ease and speed of erection, number 7, insulating properties, and number 8, fire resistance. Galvanized iron sheets or GI are made by black sheets rolled from good quality low carbon mild steels. For corrugated GI sheet, the purlin space may vary from 1.5 to 1.75 meter. An overlap of 150 mm is required. Asbestos cement sheets do not decay because of atmospheric action. These sheets are available in 1.7 meter, 2 meter and 3 meter lengths. These are manufactured in 6 mm and 7 mm thickness. For asbestos cement sheet, the purlin space may be vary from 1.4 meter to 6 mm sheets and 1.6 meter for 7 mm sheet. Number 2. Selection of bay width. A bay is defined as the space between two adjacent bands. The roof truss along with the columns constitute a band. An industrial building may have a single span or multiple spans. In most cases, the bay width may be dictated by owner requirements. Gravity control generally control the bay size. For crane buildings such as light or medium cranes, bay are approximately 4 to 8 meter may be economical because of the cost of the crane gantry girder. Number 3. Selection of structural framing system. For the purpose of structural analysis and design, industrial buildings are classified as number 1. Brace frames. In brace buildings, the trusses rest on columns with hinge type of connections and the stability is provided by bracings. Brace frames are efficient in resisting the loads and do not sway. Number 2. Unbraced frames. For unbraced frames, they are in the form of portal frames and are used mostly distinguished by its simplicity, cleanliness and economy. The frames can provide large column-free areas, offering maximum adaptability of the space inside the building. Such large-span buildings require less foundation and eliminate internal columns and drainage. They are advantageous for more effective use of steel than in simple beams, easy extension at any time, and ability to support heavy concentrated point loads. However, the disadvantages include really high material unit cost and susceptibility to differential and temperature stresses. In addition, these frames produce horizontal reactions on the foundation, which may be resisted by providing a long tie beam or by designing the foundation for this horizontal reaction. Number 4. Roof trusses. Most common types of roof trusses are pitch roof, wherein the top chord is provided with a slope in order to facilitate natural drainage of rainwater and clearance of dust accumulation. These trusses have a greater depth at the midspan. Due to this, even though the overall bending effect is larger at midspan, the chord member and web member stresses are smaller closer to the midspan and larger closer to the supports. The typical span to maximum depth ratio of pitch roof trusses are in the range of 4 to 8, the larger ratio being economical in longer spans. Pitch roof trusses may have different configurations. Meanwhile, in Pratt trusses, web members are arranged in such a way that under gravity load, the longer diagonal members are under tension and the shorter vertical members experience compression. This allows for efficient design since the shot members are under compression. Number 5. Purlins, girts, and sag rod. Purlins support roof sheeting, and loads from the sheeting are transferred to the purlins. The loads acting on the purlins are weight of roof covering and fixtures, safe weight of purlin, live load from sheeting, and wind load. For section used as purlins, number 1. Angle purlins. It is used in small shops when spacing of roof truss is between 3 to 5 meter. Number 2. Channel purlins. It is used for medium shops when spacing of roof truss is between 4 to 6 meter. Number 3. Beam purlins. It is used for heavy shops when spacing of roof truss is between 6 to 8 meter. For spacing of purlin. The spacing of purlin depends largely on the maximum safe span of the roof covering and glazing sheets. Hence, they should be less than or equal to their safe span when they are directly placed on purlins. Thus, for corrugated galvanized iron sheet, the purlin spacing may vary from 1.5 to 1.75 meter. And for corrugated asbestos cement sheet, it is limited to 1.4 meter for 6 mm thick sheets and 1.6 meter for 7 mm thick sheets. A gird is a horizontal structural member in a frame wall that provides lateral support to the wall panel to resist wind loads. The gird is commonly used as a stabilizing element to the primary structure, for example, column or post. Wall cladding fastened to the gird, or a discrete bracing system which includes the gird, can provide shear resistance in the plane of the wall along the length of the primary member. Since the girds are normally fastened to or near the exterior flange of a column, stability braces may be installed at a gird to resist rotations of the unsupported inner flange of the primary member. The gird system must be competent and adequately stiff to provide the required stabilizing resistance in addition to its role as a wall panel support. Girds are stabilized by sag rods, angle, straps, and by the wall cladding. Stabilizing rods are discrete brace members to prevent rotation of an unsupported flange of the gird. Sheet metal wall panels are usually considered to provide lateral bracing to the connected, typically exterior flange along the length of the gird. Under restricted circumstances, sheet metal wall panels are also capable of providing rotational restraint to the gird section. In general, gird support panel, panel stabilized gird, column support gird, gird stabilized column. Sag rod is a rod for preventing the sagging of an open web steel joist that is used as a purlin with its depth at right angles to a roof slope. Sag rods are usually furnished to transmit the gravity load of girds to a supporting member. Additionally, Sag rods are used to control the deflections of and stiffen girts and purlins. Sag rods are used to hold the purlins and the girts in a straight line. First, install the sag rods that connect the two purlins at the ridge of the building. Each rod must be attached from the top hole of one purlin through the bottom hole of the adjacent purlin. Use two nuts at each end of the sag rods, one on each side of each purlin. Adjust the nuts on these rods so the purlins are held straight and rigid. Next, install the sag rods between the purlins below the ridge with the rod attached from the top hole of the upper purlin through the bottom hole of the lower purlin. Use two nuts on each end, one on each side of each purlin. Follow the same procedure with the sidewall sag rods. The roof purlin should show a straight line from end to end of the building. Do not tighten the sag rods so much that the purlins are twisted out of shape. A wide variety of building types exists, ranging from major structures such as power stations and process plants to small manufacturing units. The most common type is the simple rectangular structure as shown in Figure 1. Typically single-story, which provides a weatherproof and environmentally comfortable space for carrying out manufacturing or for storage. Within a reasonable budget, a building of good appearance with moderate maintenance requirements can be achieved. Future modification can be achieved by avoiding the use of special gable frames as shown in Figure 2. Structural steel for industrial buildings. Compared to other materials, particularly reinforced or pre-stressed concrete, steel has major advantages. Its high strength to weight ratio and its high tensile and compressive strength enables steel buildings to be of relatively light construction. Steel is therefore the most suitable material for long-span roof where safe weight is of prime importance. Steel buildings can also be modified for extension or change of use due to the ease with which steel section can be connected to the existing work. Not only is steel a versatile material for the structure of a building, but a wide variety of cladding has been devised utilizing the strength developed by folding thin sheets into profile foam as shown in Figure 3. Insulated cladding systems with special coatings are now widely used for roofing and sidewall cladding. They have good appearance and durability and are capable of being speedily fixed into position. The structure of a steel building, especially of an industrial building, is quickly erected and clad, providing a weatherproof envelope which enables the floor and installation of services and internal finishes to proceed at an early stage. Since the construction schedule is always tied to the earliest handover date fixed by production planning, time saved in construction is usually very valuable. In a dry, closed environment, steel does not rust, and protection against corrosion is needed only for the erection period. For other environment protection systems are available which, depending on cost and suitable maintenance, prevent corrosion adequately. Choice of industrial building. A prospective owner may have a fully detailed design brief derived from the construction of industrial plants elsewhere. More usually, the owner is assisted in the choice of a suitable building by the completion of a detailed list of requirements so that a design brief can be prepared. Initial options in respect of preferred location, site acquisition, and environmental need must first be decided. Then, main dimension, process operation, plant layout, foundation needs, handling system, daylighting, environmental control, service routes, staffing level, and access all require definition. The preliminary selection must be made between number 1, a building specially designed for the owner. Number 2, a new factory largely built of standard structural components. Or number 3, the adaptation of an existing building. The latter may be either an advanced unit built as a speculative development or a unit which has been vacated. The location of internal columns and the internal headroom are always important, and consideration of these requirements alone may determine the choice. The advantage of freedom to plan the building to suit requirements closely and allow for future development is very valuable. However, unless there are exceptional reasons such as permanence of specific use, it is unwise to design an industrial building exclusively for a single process, since special features appropriate to the process may make redevelopment difficult. Shapes of industrial buildings. Because of its economy, the most widely used building shape is the pin-based single or multi-bay pitch roof portal frame, typically of 20 to 30 meter span at 6 meter centers, as shown in Figure 4. Hot roll eye, welded or cold form sections are usually used for the members. During recent years, an increasing use of welded section has occurred. This increase is the result of progress achieved in making welding automatic and the ability to adapt the cross-section to the internal forces. Since internal columns sterilize an appreciable space around them, their spacing may be increased by using spine I-beams to support the portal rafters. For this type of roof, the cladding is usually insulated metal decking, which may also be used for the upper side walls. Daylight is provided by profile translucent sheeting in the roof. When hot roll sections are used, haunches, as shown in Figure 5, are usually provided at the eave and the ridge. These haunches deepen the overall section, thereby reducing bolt forces. By extending the haunch regions along the rafter, the frame is also strengthened and stiffened. Lattice girders, as shown in Figure 6, are lighter than portal frame rafters for wider spans, but the additional workmanship increases fabrication costs. Based on structural requirements alone, lattice systems are likely to be cost-effective for spans above 20 meters. Roof trusses may also be used for structures which support heavy crane, as shown in Figure 7. A wide variety of structure sections may be used for lattice girders and roof trusses, including single angles, angle back-to-back, T's, H sections, or hollow sections as shown in Figure 8. For light loading, cold foam section may be used as booms with reinforcing bars as the web member as shown in Figure 9. The disadvantages of multi-bay pitch roofs are that internal gutters and rainwater disposal are required, which are a possible source of leaks, and access to the plant mounted externally on the roof is difficult. The most versatile roof shape is the nominally flat roof, covered with an insulated membrane on metal decking as shown in Figure 10. This shape allows wide freedom in plan form and eliminates the need for internal gutter, although some internal rainwater disposal may be necessary if the extent of the roof is large. The mounting and weather protection of external plant on the roof is simply achieved and access can readily be provided. Flat roofs can be supported by roll or cold form purlins on main I-beams or lattice girders. For smaller structures, the deck may span directly from one frame to another without the need for purlins. When services are extensive and there are many external plant units on the roof, castellated beams or double-layer grid space frames, as shown in Figure 11 and 12, can be very suitable for flat roof. The two-way grid distributes local loads better than any other structure form. The support for the roof deck is provided directly by the top layer and support for the services by the bottom layer of the grid. Castellated beams have a much higher moment of resistance than I-beams. The provision of daylighting in flat roof is expensive since either dome or monitor lights must be used. Flat roofs are most common for industries where daylighting requirements are minimal. Stability of industrial buildings. It is essential to ascertain the loads applied to the structure and to determine the load passed from the cladding to the purlins and side rails through the main frames to the foundations. The loads may arise from dead load, wind load, and sometimes from cranes or impact caused by forklift trucks. The overall resistance of simple single-story industrial buildings to horizontal loading is usually easy to achieve. One of the attractions of portal frame building is that in-plane stability follows from the rigidity of the frame connections. Stabilizing bracing between the portal is therefore only required in line with corresponding rafter bracing in the roof plane. For short buildings, bracing in one end bay may be sufficient. For longer buildings, bracing of two or more bays may be necessary. The rafter bracing itself provides restraint to the heads of the gable stanchions. The brace and base provide anchor points to which the longitudinal rafter stabilizing ties, which are usually the purlins, are attached. During erection, bracing facilitates plumbing and squaring of the building as well as providing essential stability. For frame with lattice girders, as shown in Figure 6, in-plane stability can be provided by connecting both top and bottom booms to the column. If the building has roof trusses as shown in Figure 7, or if only the top booms of the lattice girders are connected to the column as shown in Figure 13, the frame is effectively pinned at eaves level. To provide in-plane stability, either the column bases should be fixed or longitudinal girders should be provided in the plane of the roof as shown in Figure 14. These girders span between the gable ends, which must be braced appropriately. If the building is long or is divided by expansion joint, longitudinal bracing may not be practicable and the column must have fixed bases. Building using lattice girders or truss roof also need bracing to provide longitudinal stability. Bracing members for industrial buildings commonly use circular hollow sections, rods, or angles. When cranage is provided, the stability requirements need further examination, since longitudinal and transverse surge from the crane increases the forces in the bracing system. Steel construction is widely used for industrial buildings, including structural members such as frames, purlin, side rails, and cladding systems. Overall stability is obtained from the rigidity of connections and the use of bracing systems. A wide variety of hot roll shapes are available for structural members. More flexibility can be obtained using welded sections. Purlin and side rails may be formed from cold roll section. Types of special industrial buildings. Special industrial buildings are of two kinds. Those which are of unusual construction and those which are designed for a special industry. The main characteristic of such building is that they are invariably designed for a particular purpose or process, and are consequently virtually impossible to adapt for another kind of use. Among the former are industrial buildings which, for reasons of prestige rather than economy, utilize unusual structural forms which provide architectural expressions and thereby contribute to the visual quality of the building. Because buildings of this kind are unique, they cannot be considered generically. Among buildings designed for specific industries are heavy engineering works, aircraft hangar, power station, process plant, steel rolling mills, and breweries. Handling methods. Overhead cranes with capacity of 10 tons and more are a characteristic of heavy engineering works and power stations. They require the supports of compound columns and runway beams to carry the vertical and surge loads as shown in Figure 1. Light overhead cranes with capacity of 1 to 5 tons are a characteristics of aircraft hangars and light industries. They can be attached to the roof structure and be designed for multiple support for wide coverage, or they can be arranged to transfer laterally from bay to bay as shown in Figure 2. Roof flexibility may become important too for roof-mounted cranes used for assembly. Some years ago, so-called no-rail cranes were developed. The no-rail cranes concept inverts the overhead crane principle. Short rails are mounted in the end truck of the crane. These rails run along a series of stationary wheels. The rails are designed to be somewhat longer than the maximum distance between three adjacent support points, so that the crane is always supported by at least two wheels on each side, as shown in Figure 3. As a result of this design, the long conventional crane tracks become superfluous. The benefits of this innovative design arise both in cost saving up to 20% on the steel structure of the building and in material handling. Crane travel tracks that cross each other are feasible. Conveyors can be either floor or roof mounted. Conveyors for assembly purposes may carry appreciable weights and are of necessity suspended from the roof as shown in Figure 4. Power roller conveyors are also used for transport of bulky items and are usually floor mounted. As a result of advances in design, motorized floor transport vehicles including forklift and pallet trucks are now very common. The main influence they have on design is on the floor quality and on headroom. Automated pallet stacking by forklift trucks of specialized design may require very stringent control of fabrication and erection of the stacking racks. The racks may be incorporated in the structure of the building, such as shown in Figure 5. Daylighting. Few industries now have particular needs in respect of daylighting, since shift work is often provided for. Sidewall and roof daylighting is usually described as a percentage of the planned area. 5% giving sufficient light for bulk storage, 20% for a working process. Since artificial lighting is usually employed to establish a consistent high level of illumination, daylighting may be provided for visual comfort or for an architectural effect. The amount of services can vary in different parts of a building, from an exacting standard of air conditioning appropriate to a clean room to extensive process ductwork. The support and passage of services can be facilitated or hindered by the roof construction as shown in Figure 6. The heating of high single-story structure is always a problem, particularly when fire safety places stringent control on the temperature of the heat source. Inevitably, provisions for drainage, lighting, heating, and services such as air and electric power will conflict. They each influence the structural design. Sometimes, if services are particularly extensive, it is advantageous to use a structure form which provides abundant support for services. Maintenance. Every material used in construction has a limited life, which can usually be extended by appropriate maintenance. Maintenance is likely to be particularly important in special buildings. The design of the building should allow suitable access for the maintenance required. Maintenance may conflict with the planned usage of the building, which can easily occur if usage is intensive, as for instance, if maintenance requires dismantling or opening up, or if radiography requires areas cleared for safety. Roof maintenance is particularly important. The possible results of overflow due to rainwater outlets being blocked, either by process emissions or by snow or hail, needs to be considered in assessing the merits of the roof design, the routes for rainwater disposal, and the maintenance necessary. Due to the characteristics of the process to be carried out in a special building, it may require exceptional measures in respect of fire and explosion prevention and in fire protection and damage limitation. Sprinkler installation of exceptional capacity may be required, as well as carbon dioxide injection. Dust explosion is a risk in processes dependent on the transport of finely divided powders by conveyor or air duct. Controlling the results of an explosion is often achieved by strategically placed blow-up panels. Gas explosion can be far more destructive and difficult to control. The following are some examples of special buildings. Coal-fired power stations. A typical medium-sized power station, as shown in Figure 7 and 8, consists of a 38.6 meter span turbine hall, flanking a 13 meter span bunker bay beside a 31.5 meter span boiler house and 12 meter wide air heater building. The height of the turbine hall is typically 30 meters, determined by the servicing requirements of the turbines and generators. The height of the bunker bay, which stores several hours fuel, and that of the boiler house are similar, determined by the height of the boiler and the size of the fuel mill below, and is typically 60 meters. The length of the building depends on the number of generators installed, each having its own boiler. This type of power station is constructed almost entirely of structural steelwork and steel cladding. Steel construction is chosen because the completion of the boiler house is always on the critical path of the execution schedule. The executions of the boiler frame, designed to suit the boiler and from which the boiler is suspended, is central to the schedule. The stanchions of the boiler frame, often 6 in numbers, are typically compound H section, carrying up to 1,000 tons each, and the boiler is suspended from a heavy plate girder spanning across the stanchions. The external steelwork to the boiler house is relatively light, being mainly supported by the boiler frame, which also braces the building. In the bunker bay, which is also a steel structure, are large feed bunkers of 600 tons capacity constructed of steel plates, supported at high level, to which fuel is supplied by conveyors. There is a fire and explosion hazard in the feed conveyors and the ductwork connecting the bunker to the fuel mill and the latter to the boiler. Sprinkler and carbon dioxide fire protection is therefore required in this part of the plant, and fire protection is also applied to the steelwork. Aircraft maintenance hangar. A typical hangar bay for the maintenance of Boeing 747 aircraft, as shown in Figure 9, 10, and 11, is 76 meters wide and 97.5 meters long, and the hangar may consist of 1, 2, or 3 bays. The maximum clear height is usually 23.5 meters to allow clearance over the 20-meter high tail fin of the aircraft, but only 70 meters is required over the body and main wings. The roof may therefore have two levels, the height in the tail area being 23.5 meters, the remaining area 17 meters. The two-level roof restricts the attitude of the aircraft to nose first, whereas a full height hangar allows either nose first or tail first attitude. At the rear of the hangar is the 2 to 3 story workshop and administration block, 10 meters deep, at the same width as the hangar. The roof slope is usually small to avoid excessive height, utilizing either an insulated roof membrane on metal decking or insulated two-layer cladding. The roof structure is usually comprised of lattice trusses, girder or portal frames, but double-layer grid space frames have also been used. The main door is usually 21 meters high and can be a sliding folding or slab sliding design. The full opening width required is 80 meters. If bunching space for the doors overlaps the door opening, the bay width is increased correspondingly. Some hangar doors are only 14 meter high with a 7 meter high tailgate, or they may have a vertically folding 21 meter high center section. While some smaller hangars have been constructed in pre-stressed concrete, virtually all are now constructed in structural steelwork with insulated steel cladding. Hangars are specialized for maintenance of one type of aircraft or mix of types. Access to an aircraft because of its shape and size is a problem which is best solved by specially designed docking tailored to suit the particular aircraft. This arrangement enables a large workforce to carry out maintenance. Typically, the docking consists of main wing docks, a tail dock, and body dock. They are moved into place after the aircraft has been placed in a fixed position. Since aircraft are jacked up 1.5 meters for landing gear overhaul, it is usually necessary for the docks to have vertical adjustment. The use of wheel pits can make jacking unnecessary, but this adds considerably to cost as well as adding to specialization. Unless they can be moved out of the hangar, docks occupy a large amount of floor space. They obstruct the placing and maintenance of other types of aircraft when not in use. Consequently, tail docks and body docks are sometimes suspended from the hangar roof. Since tail docks weigh 12 to 50 tons and body docks 50 to 100 tons, provision for them must be incorporated in the roof design. Hangars are usually provided with light overhead cranes covering the full area. They are used to handle dismantled parts up to 1 ton weight. Isolated engine hoists up to 10-ton capacity may also be provided. Alternatively, the overhead cranes may be of 10-ton capacity. Conflict can arise between cranes and suspended docking. If a two-level roof is adopted, separate cranage is required in the tail bay. Electric power, air, and other services may be from roof-mounted motorized rails or in the floor. Heating is by embedded floor coils or high-power blower suspended from the floor. Blowers are large units appropriate to the height of the hangar. Sprinkler may be installed depending on the extent of the maintenance carried out and the safety procedure adopted regarding onboard fuel. Except for roof maintenance, the maintenance requirements for a hangar are usually slight. since aggressive emissions are confined to drainage from the hangar floor where painting is carried out, or from cleaning or chemical process shops. Due to the large roof area and its height, and to the characteristically exposed environment of an airport, storm damage is always possible. Roof leaks can have very serious consequences because of the high value of aircraft parts. Development in aircraft design and increased competition for contract maintenance make it necessary to allow for modification to hangar. The introduction of the 747 type and other wide-body aircraft compelled the extension of many of the hangars in use at that time. However, the intensive usage of a hangar and the strict fire and safety regulation applied when aircraft are inside makes modification difficult to carry out. Flexibility therefore needs to be allowed for at the design stage. The superiority of structural steelwork for aircraft hangar is now well established. The speed of construction, suitability for large span roof, versatility for the mounting of various services and docks, and the adaptability for future development virtually exclude other structural materials. Milk powder plant. A typical milk powder plant, as shown in figure 12, 13 and 14, consists of a spray dryer tower 18 meter by 17 meter by 32 meter high with an external boiler house, a silo and packing plant annex 16 meter by 18 meter, and a storage warehouse for packaged powder 54 meter by 54 meter with 7 meter clear height for forklift transport and stacking. The tower and annex are framed in structured steelwork with composite concrete floor and steel cladding. The warehouse typically has multi-bay short-span portal frame carrying pressed steel purlin and asbestos cement or single skin metal cladding. The spray dryer is a 10 meter diameter stainless steel drum, 14 meter high, supported at several floors. Milk and hot air are injected at the top and the dry milk powder collects in the hopper bottom. From there it is conveyed to the silos of the packing plant. The floors are lightly loaded except for ancillary plant and the spray dryer, which in operation weigh 60 tons. There is an appreciable explosion risk from the finely divided milk powder. Strong explosion ducting with an exterior blowout panel intended to control the direction and result of an explosion is incorporated in the dryer, and provision for this facility is made in the tower steelwork. The large amount of air injected in the process requires outlet cyclone to extract milk powder from the exhaust air. Even with regular maintenance, cyclones are never 100% efficient, so that some powder, which can accumulate quickly, escapes. Deposits of powder can cause problems with roof drainage, which therefore require appropriate design. Milk powder contains lactic acid, which is moderately aggressive, particularly to flat roof coating, such as asphalt and felt. Consideration of the durability of the roof is therefore required. Internally, a biologically clean environment is required in order to that the plant complies with process regulations. Easily cleanable surfaces are required internally. This requirement is best met by high-quality internal sheeting. Avoidance of surfaces which can cause lodgement of material affect the choice and detailing of any steelwork exposed internally. Competition in milk powder production requires that first cost and running costs are carefully controlled. Since development of dryer occurs, a change of dryer may be necessary involving major alterations to the tower. The use of structural steelwork and cladding facilitates cost control in both construction and modification. Industrial complex. Some major industrial projects provide both the scale and the opportunity for adapting unusual structural form, which have particular advantages. A good example of an unusual structure form is the Renault Part Distribution Center in Sweden, such as shown in Figure 15, 16, and 17. The requirement was for a single-story building of 25,000 square meters containing a warehouse, training school, showroom, and office with provision for 50% expansion. To suit the storage arrangement for the warehouse, a 24-meter by 24-meter bay was adapted, with 8-meter internal height, with 2.8% roof lighting and sidewall glazing in some areas. The main area is 4 bays wide and 9 bays long, with an additional 6 bays at one end. The structure consists of skeleton portal frames on both rectangular and diagonal axes. The main verticals are 16 meter high, 457 mm diameter circular hollow section with rod stiffener. The roof members are simple trusses formed from shaped I-beams, chambered 1.4 meter stiffened on the underside with rod bracing and short tubular verticals. Continuity between the main verticals and the trusses is established by rod bracing connecting the heads of the main verticals to the quarter points of the trusses, while the internal verticals are balanced by trusses on each side. The perimeter verticals, which have transverse and diagonal trusses on one side only, are balanced by ground anchor bracing short beam members connected to the verticals at the same level as the trusses. McAlloy bars are used for the rod stiffness to the main verticals, and steel is used for the main rod bracing. The rods are connected to the main verticals by purpose-made cast iron I-pin to lugs welded to the 457 mm diameter hollow sections, and to the trusses through sleeves set into the beam section. In each bay, the trusses are chambered to a central 4 meter by 4 meter dome roof light. The roofing consists of an insulated membrane on metal decking, which is carried on purlins between trusses. Valleys formed by the chambered trusses are drained by downpipes, incorporated in the main verticals. Both main vertical and bracing rods pass through the roof covering. The overall appearance is unusual, resembling a large marquee due to the tent-like profile of the chambered trusses and the main verticals and bracing rods protruding through the roof. Special structures are needed for some industries. They may also be provided for reasons of prestige. Cranes and conveyors carry appreciable weights and may be suspended from the roof. If services are extensive, it is advantageous to use a structural form which provides abundant support. Speed of construction, suitability for large spans, versatility for the mounting of services, and adaptability all favor the use of structural steelwork for industrial buildings. Steel construction is used for the majority of non-domestic single-story buildings. This large proportion is due to the ability to design relatively light, long-span, durable structures in steel, which are easy to erect safely and quickly. The development in steel cladding and light gauge purlin and rail system in recent years have enabled architects and engineers to create economical, attractive design for a wide range of applications and budgets. The rate of change of any activity is very rapid as technology develops. Clients expect, therefore, their buildings to have lifetime several times longer than the initial layout. A primary requirement is therefore flexibility of planning, which results in a demand for a few columns as possible. The ability to provide spans up to 60 meters, but more commonly around 30 meters, using steel has proved very popular for commercial and leisure buildings. The lightness and flexibility of this kind of steel structure reduces the sizes and the cost of foundations and makes them less sensitive to the geotechnical characteristics of the soil. The skeleton of a typical single-story building is shown in the diagram as in Figure 1. It consists of three major elements. Number 1, cladding for both roof and walls. Number 2, secondary steel to support the cladding and form framing for doors and windows. Number 3, the main frame of the structure, including all necessary bracing. In addition, the building requires foundations which have to be designed and built to transmit all the loads to the soil. Cladding. The primary functions of the cladding are to provide shade, shelter, and an attractive appearance. The cladding is therefore arguably the most important element of the structure. It is likely to be some 50% of the total cost even if a fairly basic specification is used. The frame member, both primary and secondary, are there to support the cladding and services. The requirements for walls and roof are somewhat different, although both need to be weather-tight, durable, and provide insulation. The weather tightness of the roof is clearly paramount, particularly for lower pitches. In the case of walls, the appearance will be the highest priority in making the selection. Cladding formed from metal sheets has emerged as the most popular choice since its introduction. Steel is the most usual substrate, with aluminum as a more expensive second choice. In the normal single-story building, the cladding is supported on secondary members, which transmit the loads back to the main structure steel frames. An economic solution is provided by the use of cold foam light cage sections. These sections are of proprietary shape and are produced to order on computer numerically controlled rolling machines. These processes are extremely efficient since the components are delivered to site pre-engineered to the exact requirements. As a result, fabrication and erection times are minimized and material wastage is eliminated. With high volume rolling, the material content of purlins and rail is a very significant part of the cost, and manufacturers have developed shapes which are extremely material efficient. The most common are Zs, modified Zs, and Sigma shapes as shown in Figure 2. Spans are commonly 5 to 8 meters, but longer spans up to 12 meters can be achieved. It is also traditional to use hot roll section as I or C shapes, not so sensitive to the effect of local instability. The center-to-center distance of the portal frames is then reduced, in general, to 5 or 6 meters. Generally, the cost breakdown of various elements will be cladding at 50%, purlins and rails at 10%, the main frame at 30%, and the foundations at 10%. These figures are, however, indicative, as clearly there is considerable variation in specification and cost of the cladding, which is the largest single element. The loads are transferred from the sheeting onto the purlins and rails, which in turn are supported by a primary or main structure. These loads will include such as number 1, the self weight of the cladding, of the secondary elements such as purlins and rails, and of the frame itself. Number 2, the applied loads from services and etc. Number 3, the vertical and horizontal loads from cranes. Number 4, the loads from the rains. Number 5, the loads from the wind. And number 6, the load from the earthquake effect in some areas. When the length of the structure is not too great, say 50 to 100 meter depending on temperature range, it is normal practice not to consider the effects produced by the changes of temperature. Wind can of course cause pressure, suction and drag loads on the cladding. Figure 3 illustrates the various components of load to consider in the design. The primary structure frames will normally be spaced from 5 to 8 meter centers. Although larger spacings are growing in popularity, an analysis of a purlin manufacturer sale shows that about 6 meter remains the most popular spacings. The most straightforward single-story structural form consists of a pair of vertical columns supporting a spanning beam. To be practical, there is a need for a fall in the roof finish to provide adequate drainage. For the small spans for which this arrangement is suitable, the fall can be achieved in the finishes or by a nominal slope in the beam. This form of construction is shown in Figure 4. Stability against wind loading can be provided by the cladding which is fixed from frame to frame. This simple form of structure is used for small workshops. It is only suitable for spans up to approximately 12 meters. For longer spans, this simple solution becomes in general uneconomic. Then, portal frames and lattice trusses are more competitive solutions. Figure 5 shows some options commonly used for portal frames. The more popular solutions are pin bases if there is no crane to be supported, and the fully rigid version when it is necessary to support crane loads and to obtain smaller horizontal displacement. Less weight of steel results in any case from fixed base frames, but the additional cost of the foundations of the supports can be higher than the saving of steel. Figure 6 shows an example of solid column with a typical lattice girder. Whichever solution is chosen, all loads have to be transferred to the ground in even the simplest of building. Restraint to the main structure against out-of-plane buckling can be provided by the purlins connected to the top flange of the rafter and by the rails connected to the outer column flange. Figure 7 shows 3 typical ways of providing adequate restraint. Simplest frames. The cross-section shown in Figure 4 is undoubtedly the simplest framing solution which can be used to provide structural integrity to single-story buildings. Used predominantly in spans of up to 10 meters, where flat roof construction is acceptable. The frame comprises standard hot roll section having simple or moment-resisting joints. Flat roofs are notoriously difficult to weatherproof since deflections of the horizontal crossbeam induce ponding of rainwater on the roof, which tend to penetrate the laps of the traditional cladding profiles and indeed any weakness of the exterior roofing fabric. To counteract this, either the crossmember is chambered to provide the required fall across the roof or the cladding itself is laid to a predetermined fall, again facilitating drainage of surface water off the roof. In its simplest form, the crossbeam is designed as spanning between columns. The crossbeam acts in bending due to the applied gravity loads, the compression flange being restrained either by purlin, which support the roof sheets, or by a proprietary roof deck, which may span between the main frames and which must be adequately fastened. Resistance to lateral load is achieved by the use of longitudinal wind girder, usually situated within the depth of the crossbeam. This transmits load from the top of the column to bracing in the vertical plane and hence to the foundation. The bracing is generally designed as a pin-jointed frame, in keeping with the simple joint used in the main frame. Buildings which employ the use of beam and column construction often have brickwork cladding in the vertical plane. With careful detailing, the brickwork can be designed to provide the vertical sway bracing, acting in a similar manner to the shear walls of a multi-story building. Resistance to lateral loading can also be achieved either by the use of rigid connection at the column beam joint or by designing the column as fixed base cantilever. Rigid connection and rigid column foundation joints reduce also the deflection of the beam and need less weight of structural steel for the frame. Portal frames. The two most popular arrangements are the portal frames with pin bases, if there is no crane to be supported, and the fully rigid portal frame, which is often used if there is a crane. These forms are both functional and economic. In-plane stability is derived from the provisions of moment-resisting connection at the top and at the beam-to-column connection for the first situation and also at the base in the second one. The faults required to the roof are naturally provided by the cladding carried on purlins, which in turn are supported by the main frame members. Architectural pressure leads to the use of the flatter slopes compatible with water tightness. The most common slope is about 6 degrees, but slopes as low as 1 degree have been used. Figure 8 shows a typical frame built with lattice trusses. Lattice structures are lighter than the portal alternative for spans greater than 25 meters, but the additional workmanship increases fabrication cost. Frames are normally positioned at 6 meter to 8 meter centers. This spacing generally provides economic solutions for the cold form purlin and side rail arrangements. Generally, a decision is taken early during the process of conceptual design on the types of members to be used for the lattice frame. There are many alternatives such as number 1, hollow section, in example, circular or rectangular. Number 2, traditional section, for example, angles, teeth, channel and eye sections. And number 3, the combinations of item number 1 and number 2. This selected truss should reflect not only the design aim to produce the lightest frame, but also fabrication and erection requirements. Examples of composite form are shown in Figure 10, where the booms are I sections and the internal members are rectangular hollow sections or RHS. The I sections enable easy connection of services to the truss and easy connections to columns. Bracing in the plane of the roof can be provided using simple I-plane members and simple connections, or by using the relative stiffness of an I or H section. The final decisions on the types of member to be used may be influenced by aesthetic factor and not the cost. Early industrial buildings were built with sawtooth truss layout as illustrated in Figure 11. The vertical or nearly vertical elements were glazed and north-facing to allow the maximum daylight with minimum direct sunlight. In modern times, the need for natural lighting has diminished with modern lighting system, and while 10% of area of roof lighting through translucent paint is common, many take advantage of the more reliable and controllable condition with no natural lighting at all. Generally, the columns to the frame are I or H sections, such as shown in Figure 12a. When the building incorporates an overhead traveling crane of high capacity, a build-up load or batten column may be used, such as shown in Figure 12b. In some cases, the build-up columns are continued by I sections over the level of the crane supporting structure in order to reduce the cost, such as shown in Figure 12c. Cranes. Where moving loads such as cranes and conveyors are present, such as shown in Figure 13, in addition to the gravity loads, the effect of acceleration and deceleration have to be taken into account in the design. The enhancement factors to be used depend on the particular plant and its acceleration and braking capacity. Manufacturers must be consulted where heavy, high-speed or multiple cranes are being used. To take into account dynamic effects due to cranes, the maximum vertical loads and the horizontal forces are increased. The repeated movement of a crane gives rise to fatigue conditions. Fatigue effects are restricted to the local areas of support, the crane beam itself, support bracket, and the connections to main columns. It is not normal to design the whole frame for fatigue, as the stress levels due to crane travel are relatively low. Fabrication. Important factors which must be considered at the conceptual and detailing stages are the questions of workshop facilities and space and of transport between workshops and site. While large girders and or large sections may appear to be desirable in order to reduce the number of site connections, the use of large members can often reduce the number of fabricators who can tender for a given project. The length of members available from stockists or direct from the mill can vary. When long lengths are deemed desirable, it is necessary to check their availability. Generally, standard sections can be obtained in a reasonable time, but there are likely to be delays and additional costs if non-standard sections are required. The use of slightly heavier section and standardization of section size may lead to a cheaper fabricated structure. When large prefabricated trusses are used, it may be necessary to provide lifting points or eyes, which are located to minimize stresses induced during lifting. All parts which are shop painted need to be handled very carefully to avoid damaging the coating. Lattice girders are made up of long, basically slender members and may therefore be subject to severe distortion due to welding unless care is taken during the fabrication process. It is essential that the design engineer notes that number 1, bulk orders of minimum size variation are cheaper than small orders of many different sizes. Number 2, the number of pieces to be handled should be kept to a minimum. Number 3, weld distortion and tolerances should be allowed for. Number 4, automated fabrication is generally cheaper. Number 5, careful design can minimize transportation costs. Number 6, specifications need to be realistic to reduce costs. And number 7, good quality control is essential. Transportation. In each country, there are specific lengths and widths of structures that may be transported without any problems. Example, width up to approximately 3 meter, length up to 15 meter. For larger dimension, a police notification or special permission is required. It should be noted that the various police authorities specify different periods when abnormal loads are allowed to move through their districts. Erection. In considering the erections of a framework, the designer seeks an economic but safe process. The cost of erection can be significant proportions of the cost of steelwork contract. It is often useful for a designer with little or no experience of steel erection to discuss possible solutions with a contractor. The latter will know how to build and avoid the possibility of collapse. Potentially, steelwork erection is hazardous and good control is required to ensure safety of the erectors. Lattice girders can conveniently be assembled on the ground and lifted into place. However, since cranes are likely to be used, the effect of dynamic lifting load or stress reversal should not be ignored. All steel structures are likely to require temporary bracing, which may be part of the permanent system. The temporary systems need to be carefully designed. The following factors summarize the process. Number 1. Structural steelwork erection is an operation requiring meticulous planning from conception to completion. Number 2. The operation involves many disciplines and requires cooperation and communication between all those involved. And number 3. It is an operation which is dependent upon the personal competencies of all those involved to ensure the contract is completed without accidents, on time, and within the budget. At the most basic level, single-story structures have to provide shade and shelter for designated activity in the building. Steel provides the means to obtain economical buildings with large column-free spaces. The structural system is clad to resist the weather. The cladding is supported on secondary cold form sections, which in turn are supported on the main frame. The span range is from 6 meter to 100 meter. To cover this range, structural systems are available ranging from simple beams and columns through portal frames to lattice trusses. Lateral stability can be achieved either by bracing systems or moment-resisting joints in the frames. The proportion of cost for a simple shed are approximately 50% cladding, 10% rails, 30% mainframe, and 10% foundation. Cladding systems. Steel-based cladding sheets are formed from a substrate with layers of galvanizing primer and color coating as indicated in Figure 1. For the weather phase, the coating will normally be polyvinyl chloride PVC, polyvinyl fluoride PVF, or where price is a constraint, the less durable acrylic coatings. PVC and PVF can be expected to have a life to first maintenance of 10 to 25 years depending on environmental conditions. Light colors should be used on roofs to minimize heat absorption and thermal movement. PVC should not be used in latitude less than 49 degrees. There are four main categories of cladding system. Number 1. Single skin trapezoidal such as shown in Figure 2a. Number 2. Double skin trapezoidal such as shown in Figure 3. Number 3. Standing seams or secret fix such as shown in Figure 4. And number 4. Composite panel such as shown in Figure 2b. Where double skin systems are used, the liner sheets, normally as thin as 0.4 mm, has a similar coating build-up, but with a light-colored polyester paint to the inner face. In addition to providing weather protection, the cladding provides insulation to the building. The thickness varies according to the insulation required, with typical values of 0.45 watt per meter square degree Celsius being obtained from 80 mm of fiberglass or mineral wool. The equivalent in composite panels would normally be obtained from 50 mm thickness. Roof cladding. Single skin trapezoidal roofing. This is the most basic form of cladding constructions. The main problem is to prevent condensation since it is difficult to exclude damp air from the undersides of the sheeting. The internal appearance is utilitarian since the insulation usually takes the form of unrolled thermal quilting supported on wire mesh or rigid board supported on T-bars. Double trapezoidal shell roof construction. This is the most common form of cladding both for walls and roof, with pitches down to approximately 5 degrees. It consists of a steel liner sheet fastened to the purlins or rails with an outer weather sheet held apart by Z spaces. The gap created contains insulation, normally of fiberglass or mineral fiber. Sealing of the liner skins or additions of a vapor barrier and breather membrane can be employed to improve performance in situations where there is a higher condensation risk. Manufacturers normally supply a coordinated range of accessories and roof lights to match their particular profiles. A typical construction of the system is shown in Figure 3. Standing seam and concealed fixed roofs. As steel has replaced asbestos cement in sheeting, lower roof slopes have become possible, and the appearance of buildings has greatly improved, both in form and color treatment. It is feasible to disguise the sloping roof and provide the rectangular appearance recently favored by planners, engineers, and architects who have become increasingly involved in this type of building. This development has been achieved by minimizing lapse and through fasteners. The current range of standing seam and concealed fastener system are provided in long lengths up to 32 meters with special transport arrangement and use of clips to hold the sheeting down to the purlins. The typical constructions of the system is shown in Figure 4. The outer sheeting is used to provide the weather skin in both single and double construction. Composite or sandwich panels. This is the most recently developed form of cladding and consists of panels where the insulating foam is integral with the two metal skins. The foam, which during manufacture is pumped into the space between the skins, expands to totally fill the void and adheres to both liner and outer sheet, such as shown in Figure 2b. This composite action gives robust stiff panel with the further benefit of rapid erection since the whole skin is fastened in one operation. Wall cladding. The system used for walls are similar in construction to those for roofing. Since the sheets will normally be vertical, the weatherproofing requirements are less rigorous. Another important difference compared to roof is the lower angle of incidence of the sun, allowing the full range of colors to be used without excessive surface temperatures, so giving the architects the widest possible scope for creative use of color. Given appropriate attention to joint detailing, wall cladding can be fixed horizontally, diagonally, or in combinations. The range of construction include, as for roof, single skin, double skin, and composite system, with both conventional and secret fastening. Appearance is a major consideration in the selections of the particular type to be used. Shapes of purlins and rails. Although some long-span cladding systems are available which will span up to 6 meters, most bottle frame structures are designed with purlins and rails supporting the cladding and spanning between the main frames. The spans between frames are between 4.5 and 10 meters, with 6 to 7.5 meters being most popular. Roof decks of larger span are used primarily in flat roof systems and are supported directly on the trusses. Cold form shapes. The purlins and rails are commonly supplied by specialist manufacturers who deliver pre-cut and punch cold roll items together with the necessary sag bars, cleats, or rafter stays. They have therefore developed and refined by testing a variety of shapes. The more common ones are Zs, modified Zs, and sigma shapes illustrated in Figure 7. Depending on the slope, anti-sag bars may be necessary to provide one or two intermediate support in the directions of the weak axis of the beam as shown in Figure 8. Generally, the anti-sag bars are connected using diagonal ties to the portal frames to avoid an increase of the load in the purlins at the top. Classical I-beams can also be used as purlins. I-beams and channel shapes can be used as rails. However, cold form sections are generally the most economical solution. Cold form sections manufactured from thin gauge materials are particularly prone to twisting and buckling due to factors which are directly related to the section shape. When used in service, the support system is subjected to downward loading due to dead load and live loads arising from the weight of the cladding, services, etc., and uplift if the design wind pressure is greater than the dead load of the system. Therefore, for a typical double-span system as shown in Figure 9, most of the compression flange is directly restrained laterally and against rotations by the cladding for downward loading, but it is not so restrained in the case of load reversal. Main frame bracing. Most frame configurations for larger spans have moment-resisting joints at the column roof member connections. In addition to assisting with deflection control and reducing member sizes, this arrangement provides inherent resistance to lateral in-plane loads such as those from side winds and crane movements. Bracing, both horizontal and vertical, must be provided to transfer to the foundations the horizontal loads due to wind, possibly earthquake, and out-of-plane loads. It is possible to use the cladding and wall panel instead of braces for this purpose. The bracing can be single diagonal or cross members. Bracing may be located either at mid-length of the building, such as shown in figures 13A, 14A, and 14C, or at its end, such as shown in figure 13B and 14B. Bracing at the end helps for erection purposes, since it provides a stable structure at one end of the building when the erection starts. Its disadvantage is that it prohibits the free movement of the building due to temperature, so that stresses in the members. By putting the braces at the mid-length, these disadvantages disappear since the building is able to expand freely. However, additional temporary braces should be provided during the erection stage to stabilize the first part of the building. A variety of cladding systems is available manufactured from pre-coated steel. These systems are normally supported by light gauge purlins and rails, but hot roll profiles are also used. That's all for the lesson today, and thank you.